about formation of an inner solar in black hole accretion disk. I'm Machida from National Astronomical Observatory, and my collaborator is Matsumoto-san at Chiba University. I know you all well know about the outburst, but I'd like to summarize my knowledge about outburst of black hole candidate. And this is the X-ray light curve of GX339-4. And we find the hard state around here. And we find the soft state here. And the characteristic of hard state is I skipped about this. And according to the London category, here is a power law, steep power law, and here is a hard intermediate state, and here is a hard intermediate state. But this region is no name, so these regions are very luminous hard states. And so in the outburst, the state transition comes from here to here. To compare the theoretical model, in hard state is either for Lyaf-like solution, and soft state is a standard disk solution. And when the transition occurs, the disk moves from here to here and return to here. But in this, from the observation, this region is estimated in about 40% of Eddington luminosity. And this very luminous luminosity is difficult to explain in conventional ADAF models. And so how does this bright luminosity make? So we consider the answer is formation of magnetically dominated accretion flow. So when the transition occurs, the radiative transfer becomes very important big thing. And first, the beginning of the transition, the optically thin radiative cooling becomes important. So we include the optically thin radiative. We try to simulate including the optically thin radiative cooling term. And from our numerical simulation, when the cooling includes the gas pressure becomes gas pressure decrease, and then the disk shrinks in vertical direction with magnetic energy, because the magnetic field is frozen into the gas. Then at some time the magnetic energy becomes larger than the gas pressure. Then after that, the magnetic pressure comparable to the gravity, vertical gravity, the shrinking is stopped, and the magnetically supported disk is formed. This is a result of our simulation, and the color shows the surface of plasma beta, and yellow shows the beta equal 1, and green is 10, and blue is 100. And this is the start point. So low beta region filamentary exist, and after the cooling instability occurs, the disk becomes low beta. But in the near from here to here, about 60 Schwarzschild radius from minus 60 to 60 Schwarzschild radius, and inside near the black hole, the disk still exists in the optically thin ADAF-like solution. And this low beta, this panel shows the thermal equilibrium curves with the magnetic pressure. So this low beta branch can continuously connect from the low optically thin part to the optically thick part. And this low beta disk stays in an optically thin and thermally stable new equilibrium state supported by magnetic pressure. And this low beta branch the luminosity of this low beta branch can exceed 10% of Eddington luminosity. So we consider the bright hard state is the origin of the low beta branch can be the origin of the very luminous hard state. And another characteristic of bright hard state is a low frequency QPO. And we considered in this state magnetically dominated accretion flow magnetically dominated accretion disk exists in this stage. So the gas temperature of this low beta disk is cooler than the standard ADAF conventional ADAF solution. So cooler gas accrete to the inner region, we assume. Then we carried out global MHD simulation of optically thin cooler accretion disk than ADAF. And we solved the resistive MHD equation in a cylindrical coordinate system using the anomalous resistivity like this. And general relativistic effects are incorporated in using by Schur Newtonian potential. And initial state, we assume the equilibrium torus threaded by weak toroidal magnetic field. The plasma beta at density maximum is 100. And I show the two results. The one is the high temperature case. It means the ADAF-like solution. And the other is a lower temperature model. I call the model LT is a high temperature model, and LT is a cooler disk model. And I show the result. And first, I show the time evolution of the density. This blue surface shows the ice surface of density, and green ice surface shows the vertical velocity. This value is 5% of the light speed. And inside the accretion disk, magnetic rotation MRI are driven by the magnetic turbulence, and the plasma beta becomes about 10. And this panel shows the time evolution of mass accretion rate and mass outflow rate, and quasi-steady mass accretion occur after the MRI develops. And intermittently outflow are emerging from the accretion disks. So next, I compare the model AT density distribution between model AT and model LT. Left part is the model LT, and right part shows the model low temperature model. And top panel shows the density distribution average in the dimusal direction, and bottom one shows the equatorial density distribution. And in high temperature model, the disk becomes very smooth, and matter accretes to the spiral. But in the low temperature case, constant angular momentum torus is formed around the 4 to 10 Schur radius. And this inner torus sometimes deformed in Dirac crescent shape. And the plasma beta of both models is almost 10 in this region. But so the difference is the difference of angular momentum transport rate leads this difference. So the average alpha is in the high temperature model is 0.04 or 0.46, and the low temperature model is less than 0.01. So the inner torus is formed in low temperature case. And this is the radial distribution of specific angular momentum. And red curve shows the low temperature model, and black curve shows the high temperature model. And dotted curve shows the Keplerian distribution using Biesheu's Newtonian potential. So in high temperature case, the angular momentum is sub-Kepler from inner region to outer region. But in low temperature model, we can see the constant angular momentum distribution right here. So this distribution is really constant angular momentum. And next, I show the time evolution of the inner torus. The time goes to like this. And first, this torus is a circular shape, but this is the constant angular momentum. So topoloidal sprinkled instability grows in the inner torus. Then the m equal 1 non-axisymmetric mode grows. And in same time, the MRI amplitude the magnetic field. Then when the magnetic energy becomes comparable to the gas pressure, so plasma beta becomes 1, magnetic reconnection takes place, and magnetic pressure suddenly decreases. So the topoloidal sprinkled instability suddenly dumps. So return to the circular torus, return to the circular shape, and repeat, and new generation occur. And the period of this deformation is about 1,000 unit times. If we assume the 10 solar mass black hole, the period is 0.1 second. So finally, I show the distribution of Fourier power produced by the mass accretion rate. This is the model LT and model LT. And the horizontal axis shows the radius and vertical axis shows the frequency. And we assume the 10 solar mass black hole. And in high temperature case, many significant peaks appear in many places. But so because the accretion flow don't have a characteristic radius, so many peaks appears. But in low temperature model, the specific frequency appears around the 10 Biesheu's radius, because this inner torus is formed around here. And this 10 Hz oscillation is the origin of this 10 Hz oscillation is the dynamo activity of inner torus. And finally, I show the power spectral density of the Fourier power of mass accretion rate integrated in this region. And black one is low temperature case, and blue one shows high temperature model. We can clearly see low frequency QPO here, and this is created by dynamo activity in the inner torus. And some small amplitude of high frequency QPO appear, but it doesn't grow enough. But in high temperature model, the clearly Q peaks doesn't appear in this model. So the result is same as Chris and Ken. And another important thing, the gradient between 20 to 100, the slope is steeper than the low temperature model slope is steeper than the high temperature model. So this tendency is same as the observation. So I conclude my talk. When this temperature becomes low enough, angular momentum transport rate becomes small, and constant angular momentum inner torus is formed around 10 Biesheu's radius. And this inner torus shows a crescent-shaped deformation. And this is the topoloidal sprinkled instability is origin of this deformation. And when inside the torus, magnetic field amplified by MRI, and when the magnetic field is amplified enough, magnetic reconnection takes place, and crescent shape is destroyed. And this oscillation of the inner torus forms a low frequency QPO around 10 Hz when we assume the 10 solar mass black hole. That's all. Thank you.
Question.
So I had a couple of questions. One was to clarify, so your high temperature and low temperature models that you talked about, those still include, that's with this radiatively, the optically thin radiative cooling turned on, or?
Both simulation, we ignore that optical thin radiative cooling.
Okay, so these are not cooling, so all that differs is the initial temperature of the torus,
yeah.
and otherwise they're similar? Okay. So then the other question is, have you changed resolution, numerical resolution, and confirmed that you see these same features at other resolutions? Because
yes.
as Ken showed, we see QPOs at one resolution, we go to a different resolution, we don't see the QPOs.
Yes. And so we only check the lower resolution case, but so in the lower resolution case, the high temperature model also QPO doesn't appear in the high temperature case, but in low temperature model, the QPO becomes enhanced. And
Enhanced when?
Low
Lower
resolution case. So if I have to check the high resolution case. But I think, but the reason of why the low resolution case amplify the QPO is disk temperature in low resolution case. The disk temperature is not doesn't increase enough than the higher resolution model. So why this model? Because we ignore the radiative cooling term, magnetic reconnection heated up in the inner torus. Then the inner torus is destroyed. But so low resolution case, the heat increasing of heating is not enough than this model. So when we include the radiative cooling term, so we remove the heat by the magnetic reconnection. This inner torus is continuously formed. Then these peaks appear. So we consider the resolution effect is not important.
Because I think what we had found, I think your QPOs may be related to this Papalouzoid Pringle. I mean, this very stable crescent shape that's orbiting at that radius. And if the I guess if you cool it enough that it becomes beta less than 1 or beta about 1 and you can shut off the MRI, then maybe you could still get that crescent shape, M=1 mode. But the reason I asked about the resolution, I mean, that's what Ken showed in that one plot. When we really resolve the MRI, we don't get any of these M=1, large M=1 structures.
So in high temperature case, you said I agree you said, but in low temperature model, now I ignore the low radiative cooling term, but the physics needs optically thin radiative cooling. So the heat temperature, now the magnetic reconnection adds the heat, then the inner torus destroyed. But in this time, so radiative cooling becomes important. Then the heat reduced heat removes the inner torus, then so the inner torus is not destroyed when the high resolution. We try to calculate the high resolution. I think. So, but I have to check the high resolution case, and now I try to the calculation.
What is the M associated with this dot? What is the M here?
M?
The most mode number, the azimuth mode number.
M equal 1.
Yeah. And then you were saying also that this is associated with dynamo activity. So if that's all true, then this is directly in conflict with what you were saying, right? Yes. So what are the details of the magnetic field at that point? And do you have how does the magnetic field look like?
So do you mean the average or?
For example, also yes, right. Anything?
Of course, the magnetic field is turbulent. So in small scale, the turbulent magnetic field appears, and the azimuthal part is dominant in this region. So looks like the spiral structure. In the mean magnetic field shows the spiral structure, but both same is both cases.
So is the field predominantly then of large scale?
Yeah.
So maybe that's one of the differences. And how big is what is the scale distribution in your simulations? Do you also have such a large scale magnetic field in the M=1 mode?
Well, I think that's the difference, is that at higher resolutions you don't get as large a coherence. I mean, you don't have, the field is too turbulent, there's too much small scale structure, and you break up these large scale features at higher resolutions. So that's, I mean, Mommy thinks it'll still be there when she goes and checks the higher resolution. My feeling is that it probably wouldn't be there. Unless the radiative cooling somehow gets you to, you suppress the MRI and somehow get the structure back.
So how long are the run times in both cases? And I mean, that's one possibility. If you don't run long enough, to build up a large scale field, you certainly need a lot of time. And if the resolution is higher, you need even more time than comparatively more time. And so that may kill you very easily, of course.
I don't know what her timescales are there. Just 10,000 T0, if that's
so unit time is C over C.
Right. So it's comparable to, it's tens of thousands of.
This 10,000 I calculate about million unit time.
Million time steps or
million unit times.
or orbits.
So the inner radius, about 1,000 rotational time I calculate.
Okay.
Similar length runs. And I mean, she showed it on her one plot. You know, I assume she's doing most of the analysis out after the accretion rate is kind of stabilized at some value. So I think she's in the same time regime.
All right. And then what is the boundary condition in the? It's a theta mesh, right? So it's a theta direction, isn't that right? Or the torus is contained in radius and I mean, do you have spherical polar coordinates, or what are your coordinate system? Cylindrical, yeah. So what is the boundary condition at the top and bottom of the cylinder?
So outer boundary is a free boundary condition, and the axisymmetric is averaged in the whole region. And we have a absorbing boundary condition in two splash radius.
And then top and bottom of the cylinder?
Top or bottom is also free boundary.
Free boundary.
Yeah.
What do you have?
So ours are spherical polar coordinates, and so we have a free boundary at the outer radius and essentially a free boundary at the inner radius, and then everything else is.
So free means that the magnetic field can escape somehow.
Yeah.
All right.
Alright.
So, two questions. One, the 10 hertz oscillation is that frequency is related to the production and destruction of this inner torus. Is that right? Or the crescent part of this inner torus. It's not the orbital frequency of the crescent itself, right? It's
So the 10 hertz oscillation is the frequency of dynamo activity in the torus.
right. So you build up magnetic field
Yes.
and then you reconnect
Yes.
and you destroy the inner torus, and that's what that frequency is.
Yeah.
Okay, thank you. So I understand that. So the second question is, why does magnetic reconnection destroy the inner torus? So you inject a lot of heat. Are you capturing that energy as heat?
Yes, so the when the temperature becomes temperature increase,
Yes.
the alpha becomes also increase.
Yes.
Then the accretion rate becomes mass accretion becomes fast.
Wait. The
So
increase.
alpha value becomes
So
larger
you
than
get rid of a lot of
0.01.
magnetic field, and yet you increase the stress.
Yes.
Why is that? So you reconnect a lot of the magnetic field, and yet you're increasing the
So the disk
turbulent
becomes
sources.
disk temperature becomes high.
Yeah.
Then the disk scale height also becomes high because the
Yeah.
pressure increase.
Yes.
Then the alpha also the magnetic stress also increase. Then
The total pressure shouldn't. I mean, you're turning magnetic pressure into thermal pressure, but the